on the old stuff? Any questions? Okay, so I'm working to get some stuff together for those times that I'm gone. I haven't published this module yet, but I got some stuff I'm putting together, as well as I told you I'd get you a little project to work on to help with your exam scores if you want. I'm also going to get that together. I'm hoping to get all that stuff out by Monday. So that should be done. Maybe I'll get it tomorrow if I'm lucky, but I doubt it. So let's do some new stuff. And it's actually not new. It's just an extension of what we talked about in Module 7. So in Module 7, all the stuff we were doing was talking about means, right? So we had, the idea was like, if you have one observation from a normal distribution, then we could use the z-score formula and the z-table, right? That was what we were doing then. We saw if you had multiple observations and you were calculating a sample mean, then we could still use the z-table, assuming that your sample size was big enough. We talked a little bit about that. You just had to update your z-score formula. So it was just taking into account the sample size. And so the denominator will actually get smaller because the variability decreases when you take more samples. But the process is still the same. Still use the z-table. So this was for means, right, or averages. Okay, but that's not an average is one of the most common statistics that you'll run into. People are very interested in averages, especially because they have normal distributions. But it's not the only statistic. Another statistics that you'll also see a lot are proportions, or another way, right? So proportions are the same as percentages. Okay, percentages are very often calculated or cited or reported in all sorts of applications, like, for example, when? Like, why would you be interested in estimating a percentage or a proportion?
Likelihood.
Yeah, so they're talking about probability or the likelihood. Yeah, so you might want to know you might want to try to estimate certain likelihood of events occurring. Like, if you're looking at student populations, you might want to figure out, what's the probability or what's the percentage of students that have a certain attribute, right? Does the percentage of students exceed 50% or something? More than half the people have this attribute. Where else? Percentiles we've used, but like in general percentages, a percentile itself we're not going to look at. We're not going to do inferences about percentiles. We're just going to look at percentages. Okay, so you see it anytime you're trying to figure out like percentage of a population with like a certain attribute. You see it anytime you want to do like polling. If you're trying to do polling data, right? You're looking at percentages. Trying to figure out what types of percentage support do certain candidates have, or certain proposals have, or whatever, right? So proportions are used a lot. Let me make sure I got a slide. Yeah. Okay. So we want to be able to do inference or probabilities about proportions as well as percentages, proportions and percentages as well as means. So basically, we're going to take what we did in Module 7, and now we're going to look at how that can apply to percentages as well. What's going to happen basically is we're just going to have to update the z-score formula one more time. And so we'll have like 3 different forms of the z-score. Essentially, that's what's going to happen. But some notation to get out of the way. So like we have this whole time, right, we have this idea of, there's a sample versus a population. Okay. And we've studied a couple different types of statistics up to this point. So if you're talking about a mean, right, we call the sample mean x bar. The population mean we call mu, right? We've also talked about standard deviation. All right, so for sample standard deviation, we call that S. For population standard deviation, we call that sigma, right? And we've seen those used, like mu and sigma are used in the z-score formula. So also we have similar distinctions for proportions. All right, and for proportions, for a sample, for a population proportion, we just call it little p. So it's a lowercase p. Uppercase p usually means probability. Lowercase p for proportions. And then for a sample, we use the notation p hat. And you might remember we used like a y hat back in the regression, and I told you the hat means that it was predicted or like estimated. And so hats on top of little letters in statistics pretty much always mean that it's an estimate, or it's calculated from a sample. All right. So P we use for population proportion, and then P hat, this would be the notation we'd use for sample proportion. So anytime you see a P hat, it just means sample proportion. All right, calculated from your data set. All right, so the sample proportion, I went and took quite a while to show you the different data, like I did the simulations, like the samples, and we looked at all the graphs to kind of justify the central limit theorem for means. I don't really want to go through that with proportions. You could do it. It is possible to show that proportions also will have, they'll start to take on a normal distribution if you take large enough sample sizes. So I'm hoping you'll just take my word for it. And I'm just going to tell you the central limit theorem for proportions. So that'll save us all some time and headache. And anyway, so the point is, though, that the central limit theorem, the central limit theorem does apply for proportions. So it says that, so for large enough sample sizes, then if you're going into a population and you're going to calculate a sample proportion or sample percentage, so the sampling distribution of p hat, it's approximately normal. And again, just like with the central limit theorem for the means, if you're going to talk about normal distributions, you have to know what their mean and standard deviations are. Okay? So this is like when the idea here is we're sampling from a population with the true proportion equal to p. Right, so it's kind of like we could actually know, like, if I wanted to know what percentage of people in this classroom right now have children, we could actually figure out that percentage, and we would know the true value. But then if someone else had to come in behind and they weren't allowed to talk to everyone, they were only allowed to sample a few people, they could guess based on like a small sample what the proportion is, but sometimes they'd get it wrong, right? Usually they'd either underestimate or overestimate it, just depending on who they happen to pick in their sample. So we see the same thing with sample proportions. If you take a big enough sample size, though, you will start to see that normal distribution take place. And the mean, so I'm going to use that subscript, the mean of the sample proportion will be equal to the true proportion. So on average, they'd get it right. So say the truth is that 60% of people in this room have kids or something. Well, some people are going to come in and they're going to get numbers like 45% or 50%. Some people get numbers like 60, 70%. But on average, they would get it right. You know, you get just as much underestimation as you would overestimation. And it'd be centered around the true proportion. And the standard deviation, and you're just going to have to take my word for this, and hopefully you will, is given by this formula right there. So that's the answer. So it's still a function of the sample size. It's also a function of the true proportion. Like what it turns out that things that are equally likely to occur, so like 50-50 splits, those are the least predictable things. And things that are more likely or less likely, they're actually more. It doesn't matter, but I hope you'll just take my word for it, because I'm just going to show you how to do it. I'm going to show you how to use this result, all right, rather than spend too much time bogged down in why it works. But okay, it all matters eventually. Okay, so then I'm going to show you, we can use these results with the z-table just like we did for the means. We're just going to have to update our z-score formula. So let's say, for example, that we know the truth, right? Let's say that I know that 68% of students that enroll in this class are female, And what I want to know, though, is if you randomly select 75 students, what's the probability that the sample proportion that are female will be between 60 and 70%? And I should have specified this should be 75 Math 146 students at CBC. Okay. What's the probability that they'll be between 60 and 70%? Okay. Because the truth, so this 68% right here, this is like a P. This is a true proportion. Like I know that number from past enrollments, right? But if you actually went out and you took 75 samples, what's the probability that your sample is going to be exactly 68% female if you just talk to 75 people? Are you going to get 68% in your sample? Probably not. You probably get something close, but you're probably going to get something more or less than 68%. You know, it's really unlikely that you would sample 75 people and you just happen to get a sample that looks exactly like the population. It's not very likely. Okay, so then I want to know, okay, well, what's the likelihood that you get between like 60 and 70? So this problem actually is going to look just like the Module 6 and Module 7 problems, okay, because we're going to use the central limit theorem because we have a large sample size. Okay. What we know is that the sample proportions, sometimes you'd go take a sample and you get a number less than 68%, sometimes you get more than 68%. It would have that normal distribution. It'll be centered around the truth, you know, around 0.68. Okay. And so my question is, well, what's the likelihood that you fall somewhere between 70% and 60%? So it looks just like the problem that we were doing yesterday and the day before that. Okay. Do you guys kind of understand the question I'm asking here? You know? So it's sort of gauging how often you're going to be in that range if the truth are really 68%. Okay. So what we need to do here is we know that we can calculate probabilities about a normal distribution if we use z-scores, right? So now we could do this. Now in this case we're doing an in-between probability, so what do we need? We're going to need two z-scores. The question is, what does the z-score look like? Okay, and what it looks like is we have a cutoff, right? So it's like, but our cutoff in this case is like a sample proportion, and we would need to subtract the mean and divide by the standard deviation. That's what z-scores look like, right? It's like a number minus the mean divided by the standard deviation. Well, so in the case of proportions, what happens is the mean is the true proportion, and the standard deviation is that messy square root thing that I put in the last slide. So basically, this becomes our updated z-score formula that we use when we're dealing with proportions, percentages rather than averages. Okay? So then we're going to calculate our z-score. So like if we're doing 70%, for example, so the top cutoff, 70%, then that would be our cutoff, right? The mean is 68%. And then our denominator is going to be the square root. And in the denominator, we're going to use the population proportion. We're going to use that 0.68. So, and that was just copied over, that square root mess, that was just copied over from the last slide. So it's going to be 0.68 times 1 minus 0.68, all divided by the square root of the sample size. So in this case, it was 75. So it's going to just spit out one number. It's just a little more complicated formula as to how to actually get there. This is where if you happen to have one of those teal calculators, you might want to take advantage. There's this button on them called N over D, like numerator over denominator. It's up kind of like the mid of your, it's like middle top of your calculator. You can actually use the N over D button, and it'll actually let you put the formula in so it looks exactly like this. So you can do like N over D, it'll actually create a fraction for you. And you can like fill in the numerator, and then the denominator you could put a square root, and you can even put another N over D, like another fraction into it. You could calculate this all in steps if you need to, like if that's easier. So like down at the bottom, that would be like, if you go 0.68 times 1 minus 0.68 divided by 75, and then go square root, it If my phone will unlock here, maybe. What does that denominator come out to be? Yeah, 0.0539. So yeah, so like that number on bottom, you could calculate 0.053, like you said, 9. And then 70% minus 68% is just 0.02. So you can do it in steps, like just simplify the top, simplify the bottom, and then divide. What do you get as your z-score there? Say that again. 0.37. Other people get that?
Yes.
Yeah, you can do it all at once too, and you'll get 0.37. Remember, z-scores are always rounded to 2 decimal places. Okay. So, questions about where, so far, we're not done, but questions about so far where any of those values came from? Everybody? So that's just the form, I'm just telling you right now, like this that I squiggled under, that's the z-score formula for proportions. So you just need to write it down and just use it. Okay? And hopefully you can just take my word for it that it's true. I hope you will. Okay. Then so then we have to go get the other z-score, right? So the other z-score, what's the only thing that's going to change? It's just that value that's going to change. So it's going to be 0.6 minus 0.68 because I'm doing my lower z-score, all divided. But nothing else changes, so it's still going to be the same denominator because it's always, it's a 6 right there. So in this case, it's just going to be a negative 0.08 over that 0.0539 if you have to do it in steps. And so that's going to come out to negative what? 1 point something? 1.48, 1.4. Which way does it round? 48 or 49? 1.49? 1.49. This is where you need to be careful because if you round too liberally on your denominator, you could get off by a decimal place or two in your final z-score calculation. So it's really best if you can try to figure out how to take this whole thing and just lump it into your calculator all at once because it's going to be more accurate. The less times you have to round and stop and, pull calculations out. Or you just need to keep tons of decimal places until the very end. So anyway, so that's negative 1.49 should be your z-score for that. Okay. So what do we do with those z-scores? Yeah, so since we're doing an in-between probability, 0.37, here's negative 1.49, and so we're looking for an in-between probability. So we need to go to the z-table 2 times. We'll get 2 probabilities. If you look up 0.37 on your z-table, what's the probability below that? Okay, so this will be 0.6443, and then we have to subtract the lower tail probability. So you look up negative 1.49. What's that come out to be? 0.0681. And then if you take the difference of those two, what do you get? 5762? 0.5762. Okay? So the process is the same. The z-score formula just changes a little bit because we're dealing with proportions now, percentages. And so you could do a less than probability, you could do a greater than probability. I'm not going to do all the examples for this one because this actually isn't the main point of Module 8. This is just, I want to introduce proportions. So what questions do you have on this one? This example. Any questions? Okay. So I'm just going to, real quick, I'll put it in one more little blank slide here because I just want to clarify. I think you guys get the point, but just to clarify now, right, so we have a couple scenarios, right? If it's one observation from a normal distribution, right, that's a Module 6 problem. That's just the original z-score formula, okay? If it's multiple observations and you're calculating a sample mean, sorry, that's supposed to be, I'll just erase it and redo it. And you're calculating a sample mean, which would be x bar, okay? Then you need the formula I showed you yesterday, where we update the denominator to take into account the multiple samples. And then the one we just talked about is that if you're taking in observations, that should be 2 letters there. If you're taking in observations, but you're not calculating a mean, you're calculating a sample proportion, then same process, but the z-score formula now looks like this. Right? So there's basically 3 different z-score formulas. And it's all just based on what you're doing. You know, what the application is. And of course, these are really the more applicable ones because these are the ones that involve sampling. Because the top one's interesting enough, it's just that, you know, the top one is like you're just taking one observation. Somehow you already know the distribution is normal. Somehow you already know the mean and standard deviation of that distribution. Okay, that one's not as applicable very often, except for in cases where you just know a lot about the population you're working with. All right. So then the whole point here, though, and this is the reason that we're starting to talk about, you know, these scenarios where we're taking multiple observations or we're calculating sample statistics, is because that's what you're actually going to have to do if you're doing a study. So if you go back, if you remember the big picture statistics, I've written this a couple times, but remember the whole idea is that, you know, there is some population out there, but you can't really observe it, right? It's too big, changes too often. So what do you do from that? You take a sample, right? And then, you know, this is where, so really we only have in observations to work with. You know, population is big, but we have a smaller subset to work with. So from that sample, we learned how to calculate a lot of statistics. Okay, this was the descriptive step. This is where we calculate things like X bar or the sample proportion. We looked at other things like sample standard deviation. We looked at the 5-number summary, right? All that kind of stuff. We looked at all sorts of graphs that you could form, right? So that's in the descriptive steps, just saying like, here's a sample, here's what I saw. Well, ultimately, what we're really interested in is we're interested in the inferential step. We'd like to take that information from our sample and we'd like to use it to make estimations about the parameters because, you know, you can calculate the sample mean, but what you're really probably interested in is the true mean. Or you can calculate a sample proportion, but you're really probably interested in an actual proportion. Okay, stuff like that. And the reason why is because those are the things that describe the population. All right. So now in Module 8, this is what we want to do. Okay. How do we actually do the estimate? Okay. I have a number, a sample proportion that I calculated from my data set, but I also understand that my sample probably has error in it. I didn't actually observe, you know, everyone in the population. So how do we handle that? And so we're going to learn how to estimate proportions and means. We're going to do that in Module 8. And then we'll do proportions first because they're a little easier because we can use the z-table like we know how to use. And then when we get to means, we're going to have to pull out another table, which will be great fun. So, all right. Are we ready? Okay. Let's do proportions. All right. This is going to be a whole lot of explanation, all building up to one formula. So just hang in there. All right? So here's an example of when you might want to try to use proportions. Let's suppose that your job was to determine what percentage of the residents in the Tri-Cities area are in their 20s. Simple enough task, right? Simple enough question. The task of actually figuring out, you know, what the answer to the question is a lot more complicated. So how would you do it?
Just guess.
You could guess. I think it's 17%. Boom. Right? I could do that. All right? That's one option. Do you think that's probably not the greatest estimate? I don't know. I don't know what the answer is, by the way. But what if this was like your job? Like I gave you this job and I said, hey, I will give you $10,000 in 3 months, and you come back to me and you tell me what your best guess was. Okay? Yeah, so probably the best thing you could do is somehow you would try to devise some way to take a simple random sample of residents, because you couldn't possibly talk to everyone. Okay, so you go out, you take a simple random sample of residents, and then you find out some of them are in the 20s and some of them are not. And then from that simple random sample, what would you calculate?
Standard deviation.
You could look at means and standard deviations, except for what are we actually interested in estimating here?
Oh, the torsions.
Yeah, so see, in this case, the mean and standard deviation aren't what we get. You could try to estimate the average age of residents, and that would be a mean problem. But I'm interested in the percentage. So what would we do? We'd calculate a sample proportion, right? So we would go out and we say the sample proportion in their 20s. Yeah? Okay, so you go out, you take a simple random sample. You could probably talk to a lot of people in 3 months, I'm guessing. So you go out, hopefully you use random sampling, because if you didn't, then there's a lot of ways that your results could be biased. So I don't know how you would do that. You could do an SRS of just addresses out of some directory or something, or license, go through DMV data. I don't know, whatever. Okay, but anyways, at the end of the day, you'd come back to me and you'd have a number. So let's say, for example, you did this. Let's say, for example, you went out and you managed to talk to, I don't know, how many people you think you could get? 1,000, 2,000? I don't know. Let's say you talk to like 1,000, 1,500 people or something, right? And then let's say from that sample, you come back to me and you got a sample proportion of 0.148 or something. I don't know what the answer is. Okay, but let's say that you got 14.8% of the population is in their 20s from your sample. Okay, so you come back to me, you say, okay, Ryan, I spent your money and I took a sample and this is my result. But is that actually the truth?
You gotta find out how much of it is like error.
Yeah, that's not actually the truth, is it? Even if you design a really good sample and you talk to lots of people, you didn't talk to everyone. So what are the chances that the truth is actually 14.8%? Like 0. There's like a 0 probability that you got it right, basically. So the problem is that you spend all this time and then you come back and you give me a number, but then you're also going to tell me that, okay, this is my best guess, but also it's wrong. So good. There you go. I guess that's all I can tell you, right? So what's the point, right? So this is the problem, okay? So your estimate's wrong and you know it, basically. Okay, because I didn't talk to everyone. So what do? So you mentioned error, okay? So you basically have to acknowledge that you made some error. Okay, well, how do you do that? Like how close? See, because the thing is like in our example, let's say that we got 0.48 is wrong. We know that, but is it super wrong? It's probably not like super wrong. The truth probably isn't like 2%, and the truth probably isn't like 80%. Okay? So hopefully the idea is we're close. Right? I'm probably wrong, but I'm probably close. Now the question is, so if we know that we're close, then the question is, well, what? How close? Right? So then, how close are you? So then what we do is we come through, and so we say, okay, so what we'll do is we should give ourselves some room for error, right? Because we know that we know there's error in there, right? So, if you think about it on the number line, okay, we might have gotten, if here's 0 and here's 1, our result might be right here at 0.148. So our guess might be right here. And we know we're wrong, but we think we might be in the ballpark. We think the truth could be somewhere. So what we do is we construct an interval around our estimate to give ourselves some room for error and say, okay, I know the truth's not 14.8%, but I think I'm pretty close. And so I'm going to give myself sort of an interval around that value where I think the truth probably is, if that makes sense. Okay, so this is what we're going to do, is we're going to construct an interval. That's the idea. Okay, so we'll take our number, and then we'll give ourselves some what we call margin of error, and we'll construct this interval around it where we think the truth is. So now once we decide that that's how we're going to do it, then, okay, well, what do you have to decide?
What your error is.
Yeah, how wide should the interval be? Like, am I within 1%? Am I within 2%? Am I within 10%? Right? How much room for error do you need to give yourself? That's the question. Okay, and so you decide you're going to go out. You're going to make this interval. You got to figure out how wide you're going to make it. This is where the central limit theorem. This is where that normal distribution all comes back. Because see, here's the thing. Okay, so remember that if there were some population, right? So if the population has a true proportion, P, right? So let's say like there is some true percentage of people in the Tri-Cities that are in their 20s, like right this moment, right? If you could like freeze time and then draw a border around an area that you call the Tri-Cities, and you could talk to every single person like right this instant, there is some true proportion of people that are in their 20s, like right now. Okay. All right. So then we could, if that were the case, and there was some true population proportion, what the central limit theorem tells us is that p hat is near p, and it has a normal distribution. Right? So what happens is, right, you have some true proportion. Let's say the truth is 15%. I don't know what it is. Excuse me. So in our result, we came in and we got, 0.148. Yeah? We were a little under the truth. Okay, but then if somebody else went out and did the exact same sample, what would they get? They get something different. They might come back and get 16% or something. And then if I sent someone else out to do the exact same thing, what's going to happen to them? It's different. Everyone's going to come back to me. If I gave every single person in this room this job, and even if you all did really good simple random samples, every single one of you would come back to me with a different number. Right? Okay, so then what we do is we say, well, here's what we know. What we know is that all those numbers that you're going to come back and tell me, they're all going to be somewhere around the truth. Some of you are going to overestimate the truth. Some of you are going to underestimate the truth. And I know that your observations are going to come from a normal distribution. In fact, I could even know, for example, that like 95% of the time or something, that the sample proportion will be in a certain range. Right? We could actually figure that out because we know on the normal distribution about anyways, how far out do you have to go in a normal distribution to cover 95% of it? Excuse me. It was 2 standard deviations because we had the 68, 95, 99, 7 rule, right? So we could know actually that, okay, I don't know what number you're going to come back to me with, but I know that 95% of you are going to come back to me with a number that's within 2 standard deviations of the truth. I know that because I know stuff about normal distributions. Okay, so actually what we could do is we could go to the z-table, and that's kind of an approximation. We can get better than that, right? So what we could do is we could say, all right, if we go to the z-table, we say, suppose I want to catch the truth 95% of the time with my interval. Okay. Well, what we can do then is we can go to the z-table, and we can say, okay, if the truth is right here, and I know I could figure out, where the middle 95% of data is in a normal distribution. Because if 95% has to be in the middle, how much is left for the tails? 5%? And then what do you have to do because it's symmetric? Yeah, there'd be 2.5% down here. 2.5% down here. Hey, this is actually a value we looked up before. This is actually z.025. And this is negative z.025. But what are those numbers? If you go look up on the table, go to the negative side and find the place where 0.025 is below. That's the point where 5% is below. Go to the point where 2.5% is below. We found this one already. It's exact. You see it? Negative 1.96. Go to the row with negative 1.9. Yeah. Go to the row. Negative 1.9. 0, 1, 2. Boom. There it is. It's like right here. Oh, where did it just go? There. Negative 1.96. Right? So what the z table is telling us right now is it's saying that in a normal distribution, 95% of all your observations are going to be within, it's not actually 2 standard deviations, that was just an approximation, the empirical rule. You actually don't have to go out quite 2 standard deviations, you just have to go 1.96 standard deviations. So if you go 1.96 standard deviations above and 1.96 below, you'll cover 95% of a normal distribution. So then what we do is we say, well then what we should make our confidence interval with is, this length right here. This is what we should give ourselves as our margin of error. We should give ourselves 1.96 standard deviations of error. And if we give ourselves 1.96 standard deviations of error, then even if our p hat occurs way up here at the top, we'll catch it on the bottom. And similarly, if it occurs way down here at the bottom, we'll catch it at the top of our interval. So this is how we establish margins of errors, is we use standard deviations. And the z-table tells us how many standard deviations we should go back if we want to catch it like a certain percentage of the time. Okay. So then what we do is we say, all right, we can now build something called, this is what we would call a confidence interval, basically. Okay. If you want to construct a 95% confidence interval, here's how it works. You start out with your estimate. Okay. This is my point estimate. This is what we call a point estimate. It's our single best guess. Right? Like if you have to give me one number, just give me the number that came from your sample. That's the best you can do if you have to give me one number. But we can do better than that. We can give ourselves some margin of error. So I'm going to use this. You guys ever seen the plus minus symbol? Did we use this in the class? I don't know if we've used plus or minus in this. Okay, so that's a plus or minus symbol. It means you're going to get 2 numbers out of this formula. You're going to go from your p hat, right? I showed you. We're going to go plus. We're going to give ourselves some error in the positive, and we're going to go minus. We're going to go below, right? So this formula is going to spit out 2 values. It's going to spit out a lower bound and an upper bound, basically. Okay, so we're going to plus or minus. Now, what are we going to add and subtract? What we're going to give ourselves is we're going to give ourselves that 1.96 standard deviations. So we're going to give ourselves 1.96 standard deviations. Well, what's the standard deviation of a proportion? That's where the central limit theorem comes in. Way back here. It's that square root thing. It's that nasty square root mess. That's the standard deviation. Boom. Okay. So we're going to take our estimate, and then we're going to give ourselves some wiggle room. This whole thing that you add and subtract, this, if you read polls or studies or something, this is what's called the margin of error in statistics. It's that wiggle room. It's that room for error that you give yourself because you understand that your point estimate is not 100% accurate. Okay. So, there's one problem with that formula, the way that it's written. Does anybody know? Besides, it looks like gibberish. Does anybody know what the problem with that formula is?
You have to know your population.
Yeah, what is P? It's population proportion. Well, what are we trying to estimate? We're trying to estimate the population. Like, that's what we're trying to estimate, right? See, our whole goal here, our goal is we're trying to estimate P. So how can you use a formula that requires you to know the thing you're trying to guess? Which is a problem. So what we do is essentially we say, okay, well, if you use a simple random sample, we know that our estimate is not perfect, but we know that it's close. And so it actually works pretty well that we just sub in our own estimate into the formula. And so we'll actually use p hat in the formula. And this is the 95% confidence interval for proportions. Okay. We just use our estimate in place of the population proportion because we know that we got close, even if we didn't get it exactly. And that's the best we can do. So, all right. So this is our first formula for Module 8. There's not a ton of formulas in this module, but this is one of them.
So do we use the 1.96?
Yes, the 1.96. Now this is because this is a very specific level of confidence that I'm showing you first. I'll show you how to get other confidence levels. And actually, there's a cheat sheet on your table. The bottom on the bottom of your Z table on the positive side. You see that? Oh, look at that. Levels of confidence, Z value, 1.96. Okay, so we could actually swap that out for other numbers if we wanted to go with other levels of confidence. And we'll talk later about that.
It's the same equation as for all of them.
Yeah, we'll just swap it out. So we'll talk about that. We'll probably get into that more tomorrow. I'm going to show you how to use this formula today, and then tomorrow we'll probably get into the other levels of confidence conversation. So this is, that 1.96 is just specific to what this is called a 95% confidence interval, and it's made in such a way that 95% of the time when you go out and you take a sample, you will catch the true proportion with this interval. Okay. All right. Shall we use it? Let's use it. So this is like one of those formulas you probably want to write down somewhere. Okay, so here's an example. Let's say that we get a survey of 300 people. Let's assume it's a simple random sample, but 300 people. And it says, would you be willing to pay $75 for a parking permit if you got a reserved spot on campus? So some people say yes. So then of the 300 people sampled, 127 said they would potentially be interested. So I would like to use a 95% confidence interval to estimate the true proportion of students that would be willing to pay for a permit. Okay. So there's a first step here that we need to take, because what do we need to do? Yeah, I just gave you the numbers. So how do you calculate a sample proportion from a sample? Well, how many said they'd consider it? 127. How many did I sample? 300. Okay, so first we need to get the proportion. And just for like consistency's sake, well, actually, I don't know, this one might not need rounded. What does that come out to be?
0.423.
Repeating, 423 repeating. So just for the sake of consistency, I'll keep my proportions with 4 decimals because that's what we were doing with probabilities, because that's what comes off the table. So we'll just do 4 decimals. You don't have to. You can round it if you want, but let's just keep it there. And, the more decimal places, the merrier, because it's more accurate. So we'll just go 4.4233. So about 42% of the people that we sampled were potentially interested. Of course, does that mean 42% of all students are interested? Almost certainly not. That's just our best guess. Okay. So that's why we give ourselves the margin of error. So I'll write down the formula. This is the value that we're going to take and plug into our formula. Oh, whoops, I started plugging in before I rewrote it. Let me just rewrite the whole thing first. So this is for 95% confidence. That's why there's a 1.96 there. Now I'll go ahead so now we can start filling things in. Okay. So we're going to take 0.4233, and then we're going to add and subtract the 1.96 times the square root. So wherever I see, p hat there, I'm going to plug in. And then our n was what? 300, right? Okay. So your first job is you need to calculate this thing. Don't do plus or minus. Order of operations, plus or minus is the very last thing you should do, right? Addition and subtraction, they're on the bottom of order operations. That's the last thing we're going to do is add and subtract. First, we need to figure out all this junk.
Do the right side.
Exactly. Do the right side first. Okay. So you go 0.4233 times 1 minus that, divided by 300, take the square root of that, multiply that by 1.96. So give that a try. And then hopefully we can come to some agreement about what that number is. Anybody want to take a shot? What'd you get?
0.0559.
0.559?
Yeah.
After you multiply by the 1.96? Perfect. So you should be able to, with your calculator, to take all that stuff and turn it into 0.559, you said? Yeah, if you round it to 4 decimal places. Just keep it 4 just for consistency. Okay? So this right here, this is our margin of error. So you might see it, in a newspaper or magazine or something like that. They might say, 42% of people were interested with a margin of error of 5.59%. That's one way to report this result. Okay, but for a confidence interval, we just go the extra step and we just calculate the lower and the upper bound. So we're going to get two numbers. We're going to go from 4233. We're going to subtract 0.0559. And then we're going to go from 0.4233, and we're going to add 0.0559. So we're going to take that margin of error and go down and go up. So now that's going to give us two values. So what's the lower one? 3674? Yeah. 3674?
I didn't round on that, though.
No, that's right.
3674. Okay. And then if you go up, what do you get? 4792.
Yeah.
Boom. And this is a 95% confidence interval for the true proportion based on our sample. So even though we don't know exactly what the true proportion is, we would predict that it's somewhere between 36.7% and 47.9%. Okay. So I'm going to over here. There's kind of a really specific way that confidence intervals get interpreted, so I'm just going to write that over here. So when you interpret a confidence interval, actually before I do that, does anybody have any questions about where any of those numbers came from or how we got to those final two values? So the top thing, the p-hat plus or minus, that's just the formula. It's always the same for 95% confidence for proportion. Then we're just plugging values in. Okay.
Are we going to have to interpret this?
Yes. Yeah, you should be able to interpret the confidence interval. Here's how you do it. The first thing you do is you state the confidence level, because like I said, we can change our confidence level. So we should say first, we're 95% confident. So everybody understands, what level of confidence we use to get this interval. Then you want to tell people what you were trying to estimate. So what were we trying to estimate?
Reserve parking.
Yeah, the percent of students interested in paying for a parking permit. So I've told you the confidence I use, and I've told you what I was trying to predict. Then you can report your bounds. So you say, we're 95% confident the percent of students interested in paying for a permit. Then you can say, is between, and then you report your bounds. Normally, we would go back to percent form just because that's what people understand better, but you don't have to. But that just makes more sense to a lot of people. So we're 95% confident. The true proportion of students interested in paying for apartment somewhere between 36.74% and 47.9%. Okay, and so we have an interval where we think the truth is. We have some reasonable justification for why we picked that margin of error. Goes back to the normal distribution. We can justify it. We didn't just make up a number, right? And we can use this procedure every single time.
So that's why you're less likely when your margin of error shrinks. And so if you just have your one number, you're 0% confident.
Yeah, if you just have one number, yeah, you're 0% confident that that's the truth. And you should be because you know it's not, right? And then the wider you make that interval, that's right. We could change our confidence interval, like our confidence level, but if you want to be more confident, what are you going to have to do? You're going to have to go wider probably, right? Or what else could you do? You could take more samples. So there's actually a trade-off in confidence intervals. You have the confidence level, and you can adjust that. You can be more or less confident, which is going to cause your interval to change its width. But you can compensate for that by increasing sample size. And because what you see is in the margin of error, the two things that affect your margin of error are this number, which I told you could swap out for other numbers for difficult confidence, but also this number. Because if that 300 gets bigger, you divide by a bigger number, the whole thing gets smaller. And so we'll look at that too. Yeah, go ahead.
Is there like a minimum sample size?
Yeah, technically there is, and I didn't tell you. I don't really want to, so I don't want to get too bogged down in sample sizes and stuff, but yes, there is, and it's a good point to make. If you go back to this right here, because the proportion makes a difference, typically what you want to check is you want to check to make sure that n times p times 1 minus p is at least 10. That's the rule, or in the case of sampling, you want to check that. So you want to check that if you take your sample size times the proportion times 1 minus the proportion, you typically want to see that hit about 10 or more to take advantage of the normal distribution. So it's a good question. It's a good thing to revisit and talk about because you're right. There is a sample size restriction here. I'm not really going to try to mess with you and try to give you things that don't have big enough sample sizes because I'm mostly more interested in seeing that we can actually make the calculations and get the values out of them. But it's a good thing to check when you're looking at polling data, for example, because they can spit out a margin of error, but if their sample size was too small, then actually it's meaningless. It doesn't actually mean anything if it didn't meet that sample size criteria. That's true. In this case, we're going to be fine because 300 is going to do it. You can check it. If you go 300 times this times 1 minus this,
It's like 70-something.
it comes up like 70. So you're pretty much in the clear there. But it's not a bad first step. Go 300 times 0.4233 times 1 minus 0.4233. And then you said it came out to be what?
I related it out.
That's okay. But yeah, we could try it.
73.2.
73.2 something. But at the end of the day, it's greater than or equal to 10, so you can kind of check it off a list and say, okay, this formula is probably reasonable. I could probably do this and actually have the confidence that I think I have. So, yeah. Okay. Thank you for reminding me of that. I didn't mean to list that back at the beginning. Okay. So tomorrow, when we come back, we'll look at other levels of confidence. It's quite easy. You're just going to end up swapping out that number based on your confidence level, unless you want a number that's not on this table, which is rare, but then it gets a little more complicated, but it's still doable. That's what we'll go tomorrow.